This video is on operations with radical expressions. When we add or subtract radical terms, we need to talk about like terms. In terms of radicals, that means that the radicand, the stuff under the radical, has to be the same. So the first expression here, 6 square root 3m plus 4 square root 3m, those are an example of like terms. Like terms can be added together just as if it was 6x plus 4x. We add the coefficients. And so when the terms are like, you just look at the coefficients in front, you add them, and if it was subtraction, you would just subtract. And in this case, we get 10. Just like when we're adding like terms with letters, you keep the letter. And so we're going to keep the square root of 3m. So we get 10 square root 3m. The second example here is an example of what terms look like when they are not like terms and we can't combine them. Notice the radicands here both have a 2, but one has an x and one has a y. These are not like terms, and you would not be able to simplify this expression. It is in simplest form already. So it's important for you to understand how like terms look when there are radicals involved. The radical part has to match exactly. The index and what's under the radical must be the same. So the rule is that add or subtract coefficients of like terms. Let's look at some multiplication problems. When we're multiplying, we don't need like terms. Multiplying, if you know that there's a number in front of a radical, the operation that's occurring is multiplication. So this is really just a long string of stuff being multiplied. And the rule is you multiply the stuff that's outside the radical together. So 6 times 4 is 24. And you multiply the stuff that's under the radical. You might be careful before we actually multiply it all. We know that we're going to have to simplify our answer. So we have a 3 times another 3 times an m times another m. And it turns out that to simplify this, since it's square root, I'm looking for groups of 2. And if I had written 9m squared, I probably would have had to factor that out again, like with the factor tree, to look for the groups. But I already have them here. Now that won't always be the case. Sometimes you'll just multiply it and then break it down. But we have a group of 3's. That means a 3 comes out. That gets multiplied to what's already in front. And a group of m's. So an m comes out. 24 times 3 is 72, and so we get 72m. Notice there's nothing left that didn't group up, so I don't need the radical in my answer. Now, this sort of looked like terms. We didn't need them to be able to multiply. So in this next case, we see that they're not like terms, but because it's multiplication, it doesn't matter. We take the numbers outside the radical, we multiply them together. We take the numbers under, or letters, under the radical, and we multiply those. Remember that since it's square root, we like pairs, so I'm not going to multiply that 2 times the other 2. I'll leave it because I'm going to circle that group. But I have to account for everything that's under both radicals. So I have the x from here and the y from here. Since I have a group of 2's, I'll go ahead and circle those. And since a 2 is coming out, 35 times 2 is 70. X and y didn't pair up, those stay under the radical. Watch out for cases like this last example. It's okay that I don't have like terms. What I can't do is put different indexes. remember that there's a 2 there if there's not anything written. I can't combine these under the same radical symbol because one is a square root and one is a cubed root. So even though I would like to, there's nothing that I can do to this problem except for possibly multiply the stuff that's outside the radical. I can do 5 times 7 and get 35, but my radicals have to stay separate because one's a square root and one's a cubed root. And so this is as simple as you could make this answer, and it doesn't really look very simple, but it is simplest form. The last thing we're going to look at is dividing. We've done the addition and subtraction. The last screen was multiplication. For dividing radicals, we're really talking about rationalizing the denominator. Remember when we worked with I, we weren't allowed to have I in the denominator. The reason is because I is a radical. Remember, I is the square root of -1. And so the rules of math say we're not allowed to leave our answer with a radical in the denominator. To get past that, we take it, and since we don't have anything to conjugate like we did with the I, we're going to think about what would make this square root disappear. Well, there's something that you need to remember from using square roots before. If you square and take the square root of something, squaring and square rooting are inverse operations. And so they sort of cancel each other out and leave you with whatever it was you started with. So the square root of x squared is x. The square root of 5 squared is 5. The square root of the quantity 2y squared is just 2y. So as long as the same thing is being squared and square rooted, we end up with just what it was happening to. If we use that concept over here, I could get rid of this radical by multiplying it by another square root of 3x, because that means square root of 3x squared. But what I do to the bottom, I have to do to the top. So on top, 7 times square root of 3x, one's outside the radical, one's inside. There's nothing I can do with it but write it next to each other. On the bottom, the square root of 3x times the square root of 3x, you can use your rule. Remember, squaring something is the same as multiplying it by itself. But even if you didn't notice that, look what would happen. We'd get square root of 3 times 3 is 9, x times x is x squared. And you can simplify that because the square root of 9 is 3. And the square root of x squared, well, that's one group of x's. And so you can see how the 3x just pulls out of the radical by doing that. This is our final answer. The entire point is to get rid of the radical in the denominator. Let's look at the next one together and maybe it'll become clearer. This is usually the hardest concept for most students. Remember, you only want to get rid of the radical. So this x is allowed to be there. I know that if I multiply by the square root of 6, square root of 6 times square root of 6 will just give me 6 plain without the radical. What I do to the bottom, I do to the top because this is multiplying the whole thing by something equivalent to 1. Since those are both under the radical, I can multiply them together under one radical. So this is 2 square root 18. We're going to have to simplify that, but for now, let's take a look at what's left on the bottom. Square root of 6 times square root of 6 is 6, and I still have an x. Notice I put the number in front. We're just used to seeing it that way. So there's a few things that have to happen at this point. If you end up with any radical that's not in simplest form, you need to put it in simplest form and do your tree and simplify. 18 is 9 times 2, which is 3 times 3 times 2. We get a 3 that comes out. That gets multiplied to the 2 that's already there. This gives me 6 square root 2 in the numerator. I also still have a 6x in the denominator. Notice those 6's, neither one of them is under the radical. I can cancel them because 6 over 6 is 1. Never ever cancel something that is under the radical with something that is not under the radical. You always have to have either both under or both not to be able to cancel them. We'll practice more of these in class. I recognize that this is probably the harder of the concepts covered in this video. Our summary is to add and subtract using like terms, just the way you would for any other kind of like terms. When multiplying, we keep keeping stuff that's outside the radical outside and stuff that's inside the radical inside, and then simplify if needed. We rationalize to remove any radical from the denominator of a fraction. Always simplify in the end as much as possible.